We stand at the threshold of a paradox. The Cryogenian, 720 to 635 million years ago, an epoch whose etymology, cryos, cold, genesis, birth, already encodes its drama. This is not a mere frozen chapter of the Earth. It is a geodynamic, climatic, and biospheric crucible. In this narrative I will map its rhythms, orbital and tectonic drivers, isotopic fingerprints, sedimentary architectures, and the cascading evolutionary consequences that culminated in the late Neoproterozoic rejuvenation. Expect technical fidelity, absolute numerical detail where it matters, and a touch of speculative texture that reframes old puzzles in new lights. First, chronology and stratigraphic framing. The Cryogenian was ratified by the International Commission on Stratigraphy in 1990, but its base is unconventional, defined by a fixed radiometric age, currently 720 Ma, a revision settled in 2015. This contrasts with biostratigraphic markers like Treptichinus pedum at the Cambrian base. The consequence, the Cryogenian's lower boundary is tied to UPB zircon ages and their inherent analytical uncertainties. Precision often plus or minus 1 to 2 Ma in high-quality shrimp or ID-TIMS datasets, but reproducibility across laboratories and detrital inheritance can introduce systematic offsets. Therefore, when we discuss the Sturtian onset at approximately 720 Ma, we must keep uncertainty envelopes in view, plus or minus 1 to 3 Ma for primary tufts, larger for detrital-dominated units. Two global-scale glaciations dominate: Sturtian, approximately equals 720 to 660 Ma, and Marinoan, terminating approximately equals 635 Ma. The durations differ. Sturtian's longevity approaches approximately 60 Ma, Marinoan is shorter but intense. The glacial deposits, tillites, diamictites, dropstones, occurring at low paleolatitude are the empirical backbone of snowball hypotheses. Paleomagnetic inclinations from key sections suggest glacial diamictites at paleolatitudes of less than 30 degrees for several regions. Yet magnetic overprints and inclination shallowing require rigorous correction. When corrected, multiple global datasets still indicate low-latitude ice, but the debate persists: full planetary sea ice versus equatorial refugia, slushball. To adjudicate, we must synthesize paleomagnetics, cap carbonate geochemistry, and global climate modeling. Isotopic excursions are diagnostic. The Cryogenian hosts some of the largest negative delta-13C anomalies in Earth's history. Pre and Sin glacial values plunge from typical Neoproterozoic plus 0 per mil to strongly negative values, often -5 per mil to -10 per mil in carbonate sequences, followed by extreme positive rebounds in cap carbonates. The Marinoan cap carbonates exhibit striking delta-13C recovery spikes exceeding +10 per mil in some localities, signals implicating massive organic carbon burial or rapid carbonate precipitation under high alkalinity. The geochemical choreography suggests glaciation-induced perturbation of global carbon reservoirs. Suppressed primary productivity during full glacial phases, episodic explosive photic zone recovery, and post-glacial weathering-driven alkalinity pulses leading to cap carbonate deposition. Oxygenation dynamics. Cryogenian oxygen geometry is nuanced. Bulk marine redox proxies, phase speciation, MOU enrichments, indicate widespread anoxia, particularly during interglacial intervals between Sturtian and Marinoan. However, molybdenum and uranium enrichments correlate with increased continental weathering and nutrient fluxes during deglaciation, implying transient oxygenation events in shelf environments. The net effect: oxygen sinks expanded under low productivity and restricted shelf circulation, but deglacial pulses could have driven ephemeral oxycable environments, critical for eukaryotic expansion. Tectonics and paleogeography form the stage. Rodinia rifted from approximately 750 Ma, generating rifted margins, increased continental weatherability, and voluminous mafic emplacement. The breakup elevated global silicate weathering in some models, but more importantly, rifting created shallow epicontinental seas that alternated between stratified, anoxic basins and oxygenated shelves. Crustal fragmentation likely revised ocean chemistry. Enhanced alkalinity in some basins favored widespread dolomitization and cap carbonate precipitation during deglaciation. The interplay of rift-driven CO2 drawdown through enhanced seafloor hydrothermal fluxes and weathering controls requires coupled mantle crust climate models to resolve. Mechanisms for cryogenian glaciations. Multiple forcing hypotheses coexist. A favored route to runaway glaciation begins with lowered atmospheric PCO2, via enhanced silicate weathering from rift-generated fresh basalt, organic carbon sequestration, or burial associated with expanded carbonate shelves, reducing greenhouse forcing below a threshold where ice albedo feedback leads to near-global glaciation. Solar luminosity at approximately 700 Ma was approximately 0.99 of present, a minor but non-negligible factor. Feedbacks such as reduced atmospheric water vapor and changes in cloud properties intensified cooling. Conversely, deglaciation mechanisms center on volcanic CO2 accumulation under an ice-covered ocean and suppressed silicate weathering, timescales of approximately 10⁵ to 10⁶ years to reach radiative forcing sufficient to destabilize global ice. The accumulated PCO2 in snowball scenarios may have exceeded several tenths of a bar, a gargantuan perturbation reflected by cap carbonate fabrics formed under extremely alkaline, supersaturated conditions. Sea level and stratigraphic markers. Glaciation-driven eustacy is evident in stacked diamictites and interbedded shallow marine carbonates. Sea level oscillations on 10⁻⁴ to the power of 6-year timescales can be inferred from facies successions, tillites grading into glaciamarine rhythmites and rhythmites capped by laminated cap carbonates with cementation fabrics indicative of rapid carbonate precipitation. The Cryogenian interglacial interval, between the two major glaciations, records marine transgression and anoxia, with black shales and laminated anoxic facies and isotopically light organic carbon. Biosphere response. Phylogenetic and ecological consequences of cryogenian stresses were profound. Testate amoebae, Archelinida, first appear in the record in this interval, a subtle but meaningful increase in morphological complexity among protists. Proposed cryogenian sponge-like biomarkers and putative sponge body fossils are contentious. Sterane signatures and hexactinellid-like spicules claimed from cryogenian strata rest on low abundances and diagenetic ambiguity. Yet, if crown group sponges existed, their presence implies deep metabolic and ecological reorganization prior to the Ediacaran. More robust is the diversification of unicellular algae, Archaeplastida, whose biomass explosion by factors estimated between 10⁻²⁰ and 10⁻³ would reshape nutrient cycles and organic carbon export. The genesis of heterotrophic planktonic trophic modes at the cryogenian close further dismantled prokaryotic predominance, enabling more complex food webs in the Ediacaran. Mass extinction versus turnover. Cryogenian glaciations likely induced severe reductions in shallow marine primary production, but extinction patterns are non-uniform. Low diversity assemblages between glaciations hint at bottlenecks followed by adaptive radiation in refugia, equatorial open water zones, sub-ice chemoautotrophic oases, or hydrothermal ecosystems. Molecular clock assessments for major eukaryotic clades show deep divergences clustered around the Neoproterozoic, but calibration uncertainties persist. The cryogenian's role may be that of a selective sieve, pruning opportunistic lineages while favoring groups capable of dormancy, photophysiological flexibility, or heterotrophy. Sedimentology offers micro-architectural clues. Cryogenian cap carbonates display isotropically laminated micritic fabrics, teepee structures, and giant wave-generated dolomitic beds. Microscale carbonate cements, micrite mosaics with primary delta-13C excursions, point to episodic alkalinity spikes. Dolomite occurrences in Cryogenian successions are widespread and temporally clustered, perhaps linked to Mg/Ca shifts or microbial mediation during deglaciation. Cryogenic dropstones embedded in finely laminated oxy anoxic couplets testify to episodic ice rafting against otherwise low-energy basins. Climate modeling advances have sharpened debates. GCMs coupled with dynamic ice sheets reproduce snowball states under reduced PCO2 and realistic orbital forcing, but microphysical treatments of sea ice albedo, brine rejection, and ocean stratification alter thresholds substantially. Slushball scenarios gain traction in models allowing narrow equatorial polyneus maintained by upwelling heat. These provide refugia for photosynthesis, yet still produce low-latitude diamictites through iceberg carving from mountain glaciers. The models underscore timescale sensitivity. Bifurcation points and hysteresis yield alternative stable states. Small parameter shifts change outcomes dramatically. Trace element systems and redox-sensitive isotopes provide further windows. Molybdenum and uranium enrichments in post-glacial caps suggest oxygenated shelf sinks during early deglacial intervals. Conversely, sulfur isotopes, delta-34s, show expanded fractionation implying altered sulfate reservoirs during glaciations. Iron speciation in shales indicates variable ferruginous versus eutinic conditions across basins, consistent with spatially heterogeneous redox landscapes rather than a monolithic global state. Finally, consider the Cryogenian as an evolutionary and geochemical hinge. The accumulation and catastrophic release of CO2, the oscillation of redox and nutrient regimes, and the tectonic remodeling of continental margins collectively forged conditions for the Ediacaran radiation. The Cryogenian's cold paradox, planetary sterilization versus evolutionary impetus, resolves into a nuanced narrative. Environmental extremes that imposed severe selection pressures but also created ecological vacancies and chemical landscapes conducive to innovation. In closing, reinterpretations of Cryogenian data require integrative workflows, high-precision geochronology anchored to stratotypes, multi-proxy isotopic and elemental geochemistry across global transects, refined paleomagnetic reconstructions with robust demagnetization and fold tests, and climate model ensembles that sample parameter uncertainties. Only by weaving these threads can we quantify the amplitude, duration, and ecological consequences of cryogenian perturbations to within meaningful confidence intervals. The Cryogenian remains a frontier, an interval where Earth's systems were pushed to nonlinear edges and, in doing so, reset the biosphere's trajectory. Its frozen deserts and explosive rebounds are not merely relics in the stratigraphic record, they are experiment stations illustrating how planetary-scale stressor can both prune and fertilize the tree of life. As we probe its signatures deeper, one zircon, one delta-13C excursion, one diamictite layer at a time, we come closer to resolving whether the planet experienced a complete snowball, a slushy middle ground, or a mosaic of extremes. What is clear is that the Cryogenian's cold birth was a crucible of tectonic, chemical, and biological transformation whose legacy echoes through the subsequent rise of complex life.